Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at polynomials with real coefficients. So, in this topic, we will examine the properties of roots of polynomials with real coefficients. We will look at some examples, and we will emphasize that the result we will see in this topic is one of the most important results you will see in this course. Now, a polynomial with real coefficients is any polynomial where all the coefficients are real. Easy enough. For example, here we see such a polynomial. So even though the variable z could take on a complex value, all of the coefficients are real. Now, any polynomial of degree n may be written as follows. P as a function of the variable z is the sum of alpha sub k, the kth coefficient, times z to the k, where k goes from 0 to n being the degree. So expanded out, this polynomial would look as follows. And of course, we are assuming that the coefficient of the leading term is indeed non-zero. Now, it's important to note that in this course, the coefficient of z to the k will always be subscripted, such as alpha sub k. So, alpha sub 0 will always be the constant coefficient. Alpha sub 2 will always be the coefficient of z squared. Now, before we go ahead, let us review some of the relevant properties of complex conjugates. First of all, for any complex z, the conjugate of the conjugate is the value itself. So z double star is equal to z. For any real number alpha, alpha star, or the conjugate of alpha, is equal to alpha itself. The conjugate of a sum is the sum of the conjugates. So what's nice here is that we can actually generalize this. If we have a finite sum where we are summing, in this case, n different terms and taking the conjugate thereof, then this is equal to that same sum of the conjugates of the individual terms. Also, for the product of two complex numbers, the conjugate of the product is the product of the conjugates. And for a complex number raised to an integer exponent, well, actually any real exponent, but we've only proved it for integers, z to the n conjugated is equal to the conjugate of z raised to the power n. Now, suppose that r is the root of a complex polynomial of degree n with real coefficients. So r is some complex number, and when we substitute it into the polynomial, we get the value 0. We have two possibilities. Either r is real or r is complex and not real. Well, let us assume that r is not real. So, let us assume that r is a non-real root of p, in which case, let us conjugate both sides of that equation. So, we have the conjugate of the sum equals the conjugate of 0. Now, from the properties of the conjugate, the conjugate of a sum is the sum of the conjugates, so we can bring the conjugate into the sum. The conjugate of 0 is 0. Now, on the left-hand side, we have every term being a product of a coefficient and r raised to some power. So the conjugate of a product is equal to the product of the conjugates. So therefore we can bring the conjugate into the product. All right, now wait a second. We assumed all the coefficients of the polynomial are real. So each a sub k, or alpha sub k, is real, and therefore alpha sub k star is equal to alpha sub k. Okay, that's one simplification. The other simplification is that r to the k conjugated is equal to the conjugate of r raised to the power k. Let's make both those simplifications. Oh, but wait a second. Is the left-hand side not the original polynomial evaluated at r star? Well, if it is, and it is, we see that r star is also a root of the polynomial p. So consequently, if r is a root of a polynomial with real coefficients and r is not real, then r star is also a root. So now let's do this as a proof. Theorem. If p is a polynomial with real coefficients and r is a root, then so is the conjugate of r. Proof. Let us assume that if we evaluate p at r, we get the result 0. Now, if we evaluate p at the conjugate of r, we get that that is equal to the sum of alpha sub k times r star raised to the power k. But we know that the conjugate of r raised to the power k is equal to r to the k conjugated. So let's do that. Additionally, alpha sub k is equal to alpha sub k star because alpha sub k is real. Now we have a product of two conjugates which is equal to the conjugate of the product. We have here a sum of conjugates which is equal to the conjugate of the sum. But wait a second, the sum inside the conjugate is what we assumed was equal to 0, and 0 conjugated is 0, and therefore p at r star is equal to 0 as well. Now, to reiterate, if p is a polynomial with real coefficients and r is a non-real complex root of p, then r star is also a distinct root of p. Now, we will describe r and r star together as a complex conjugate pair. This is a term we will use throughout this class and you will use throughout your undergraduate career. So, any non-real complex number together with its conjugate form a complex conjugate pair of numbers. Now, more generally, if p is a polynomial with real coefficients and r is a non-real complex root with multiplicity m, then r star is also a root of p, also with multiplicity m. Now, this is a result that we did not show in this class, but you should be able to deduce this, or at least it should make sense that this is true. Now, note that if the coefficients of the polynomial are not real, the correct statement is as follows. If r is a root of the polynomial p, then r star is a root of the polynomial with a conjugate of the coefficients of p. Okay, so that's a more general statement. So for example, it happens that r is equal to 2 minus j is a root of the polynomial z squared plus 1 minus 4j all times z minus 1 plus 13j. As you can see, this is a polynomial that has complex and non-real coefficients. You can check that the conjugate r star 2 plus j is a root of the polynomial z squared plus 1 plus 4jz minus 1 minus 13j. So I've taken the conjugate of both of those coefficients. And of course the conjugate of the leading one is 1. If I was to substitute or evaluate the first polynomial at the conjugate of r, that is, if I was to evaluate that first polynomial at 2 plus j, the result is 8 plus 10j, and that is not 0. So while 2 minus j is a root of the first polynomial, 2 plus j is not. Now, to demonstrate, we already know that the roots of z squared plus 1 are j and negative j, and negative j is the conjugate of j and vice versa. Let's take a look at the polynomial z squared plus bz plus c. In this case, we can find the roots using the quadratic formula. Now, I've substituted these values into the quadratic formula and expanded them, but notice that we have negative b over 2 plus or minus the square root of something over 2. Okay, now if b squared minus 4c is greater than 0, then both roots are real. If b squared minus 4ac is less than 0, then 4c minus b squared is greater than 0, and we see therefore the roots are negative b over 2 plus or minus a real coefficient times j. Well, when you have negative b over 2 plus that coefficient times j, the conjugate of that is negative b over 2 minus that same coefficient times j. So yes, we see that with a quadratic, if the coefficients are real, then the roots are either real or they come in complex conjugate pairs. Just to give a few more not so obvious examples, here is a quintic. This polynomial must have 5 roots, all the coefficients are real, and consequently all of the roots must either be real or come in complex conjugate pairs. In this case, there are 2 complex conjugate pairs of roots and 1 real root, and the roots are shown in the image or on the complex plane at the right hand side. Here's a slightly different polynomial, and if we find the roots of this polynomial, we note that 3 of the roots are real and there's only 1 complex conjugate pair of roots. And once again, these roots are shown here on the graph on the right. Now, following this topic, you understand the significance of the roots of a polynomial with real coefficients. That is, the roots are either real or come in complex conjugate pairs. You've been exposed to the proof, you are aware of some examples of this result, and by how often I re-emphasized it, hopefully you should be aware that this is one of the most significant results in this course. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!